Good afternoon, everyone. Thank you to be here today and welcome to the third Enables webinar, where we will try to give you an overview on present status, trends, and next challenges of lithium-based batteries, the electrochemical energy storage device which revolutionized modern power sources. I am Claudio Gerbaldi, leader of the Game Lab group at the Politecnico di Torino, Italy, and I'm glad to introduce you the three colleagues who have been so kind to accept my invitation to share the stage for this webinar today. Dr. Francesca Colò, postdoc researcher in my group at the Politecnico di Torino for polymer electrolyte development. Then my colleague from Rome La Sapienza University, Professor Sergio Brutti, who has almost 20 years experience in solid-state chemistry and thermodynamics for the development of advanced energy storage materials. And then Dr. Matteo Destro, who is researcher at FAAM-Lithops batteries, where he is responsible for testing and development of innovative materials for lithium-ion technology. Here you have some useful information regarding today's webinar. And here you have today's objectives and outline. The talk is about 40 minutes and will chiefly focus on materials viewpoint. I will start with a brief introduction, firstly recalling the aim of European project Enables, and then rapidly describing the main characteristics and working principles of lithium-ion cells. After this, we will have the core of the webinar with Professor Brutti and Dr. Colò, who will focus on electrode and electrolyte materials respectively, and Dr. Destro for final insights on the industrial perspective and related issues. After the recorded webinar ends, we will be back live for question time. Okay, so let's start with a brief introduction on Enables European project, in which we are partners for the joint research activity. By the year 2025, there will be 1 trillion IoT devices worldwide that need power. The challenge is to eliminate or significantly reduce the need for battery replacement by developing energy harvesting and energy storage solution, while also reducing the IoT device energy consumption. Through providing easy access to key infrastructure and expertise, Enables will bring researchers and industry users together to develop application-oriented solutions for IoT devices and systems. Enables is a 5.2 million euro research infrastructure project that started in January 2018. With the specific mission to create access to research infrastructure, thus allowing self-sustaining energy solutions to power the Internet of Things. Solutions that are based on energy harvesting, storage, micropower management, and system integration activities. Simulations, data libraries, equipment, and expertise access, along with feasibility studies, can all be accessed in a fast-track manner via Transnational Access, TA, and Virtual Access, VA program. Enables also funds joint research activities, JRAs, between partners that are designed to improve the technology on offer through both TA and VA. To address this, academic and industry developers need to work together to collaboratively develop application-oriented solutions. Enables addresses this by building an ecosystem for collaboration, initially creating a starting community. It provides external fast-track access to expertise and laboratories with over 130 researchers and over 2 billion euro worth infrastructure technology on offer through both VA and TA. Transnational access funding is there to facilitate free-of-charge access by the user community to expertise and infrastructure of the Enables partners to do initial feasibility studies. A typical TA project is of the order of 10 to 20 days of work. TA is complemented by GRAs to facilitate internal collaborations between partners and networking activities to accelerate collaboration between the stakeholders and accelerate the development of application-oriented power IoT solutions. GRA tasks aim to pushing the state-of-art as well as providing all data and measurement methodologies necessary for benchmarking, specification, and template standards. GRA activities comprise the technology pillars of energy harvesting, energy storage, power management, and system integration, and are strongly interrelated one with each other. Enables provides fully funded access to key European research infrastructures and is open to industry and academia. This collaborative approach will help bridging the gap between capturing ambient energy supply from energy harvesting sources, integrating new devices for energy storage, and developing micropower management solutions for miniaturized system operation. The question is, how do I apply for access? Actually, a very simple online service for applying for transnational access is available through the Enables website. Just sign up and inquire or write for more infos to Paul Rosengrave from Tyndall. Libraries of parts based on methodology and or simulation files will also be available. In the second part of the introductory section, I will share with you a very non-comprehensive overview on lithium-based batteries and related working principles and main components. Most of you well knows about the trend in the use of energy nowadays. Actually, not during this lockdown, but the point is that energy consumption will grow exponentially in the coming years. And for sure, the need for a sustainable future is moving faster and faster towards sustainable energy. But the alternative energy renewable sources are intermittent sources of energy, thus require convenient energy storage system to store the surplus energy they provide. Actually, they need batteries, and in fact, always higher energy and power density batteries, which are also fundamental for next generation electric and hybrid electric vehicles. Power to go. That's the promise batteries deliver. They give us all the convenience of electricity in a handy portable form. The only trouble is, most batteries run flat very quickly, and unless you use a specialized charger, you then have to throw them away. It's hard on your pocket and bad for the environment as well. Actually, we throw away billions of disposable batteries every single year. Rechargeable batteries help to solve this problem, and the best of those are based on the technology called lithium-ion. Our cell phones and laptop computers all use lithium-ion batteries. They have been in widespread use since about 1990s, launched on the market by Sony, with the basic chemistry developed by Professor Goodenough and Whittingham and Dr. Yoshino, who have been jointly awarded with the 2019 Nobel Prize in Chemistry. Let's take a closer look at how they work. The key components are intercalation or insertion electrodes that can reversibly store lithium in the form of ions, and the electrolyte, which plays a key role physically separating the two electrodes and allowing ions to move back and forth. When a lithium-ion battery is fully charged, all the lithium ions are stored between the layers of graphene in the graphite electrode, the anode. They have all moved over the right on top here. In this charged state, the battery is effectively a multi-layer sandwich where graphene layers alternate with lithium-ion layers. As the battery discharges, the ions migrate from the graphite electrode to the cobalt oxide electrode, from right to left. When it's fully discharged, all the lithium ions have moved over the cobalt oxide electrode cathode on the right. Once again, the lithium ions sit in layers, in between layers of cobalt ions in red and oxide ions. As the battery charges and discharges, the lithium ions shunt back and forth from one electrode to the other. Here you have a slide which summarizes the main components of a standard lithium-ion cell. Like any other battery, a rechargeable lithium-ion battery is made of one or more power-generating compartments called cells. Each cell has essentially three main components: the cathode, the anode, and the electrolyte. Electrodes are generally composite, including active materials, conducting additives, and binders, and are supported on metal current collectors made of aluminum for the cathode and copper for the anode. The electrolyte is generally a liquid mixture of organic carbonate solvents with dissolved lithium salt, which are soaked on a polyethyl olefin separator. And then we have several other components comprising also safety tools. More details on electrodes and electrolyte will be given by the colleagues later on, and an extensive reference section is provided at the end of the presentation for you to deepen any single aspect of the lithium-ion battery. I would just conclude this introduction by giving you some hints on where research is moving to develop the next generation batteries. Next generation batteries should take all the advantages of lithium-ion batteries that are perfect for mobile devices and bringing those to the next stage, to, at least, double the energy density and power delivered, which will allow electric transportation and large-scale renewable energy plants to be really effective. The roadmap for next-generation lithium-based batteries includes lithium-sulfur and lithium-air batteries, mainly for automotive purpose, but in all cases, all solid-state technologies. So with solid-state electrolyte, which are fundamental to achieve the goals while also assuring required safety. And then, besides lithium, we have several novel disruptive technologies like those sketched here on the right, including different alkali metal ions, multivalent cations, and also salt water and paper, and which will be the focus of a following Enables webinar around the end of the year. With this, I conclude. Let's move to the core of this webinar. Now, section 1 on advanced lithium-ion active electrode materials, discussed by Professor Brutti.
The two key properties of electrode materials for lithium-ion batteries are the theoretical capacities and the redox potential. The first is the number of electrons that can be theoretically exchanged during the redox reaction, and the second one is the redox potential at which the lithium incorporation, the incorporation reaction, takes place. If we combine these two properties in the so-called Ragone plot, we can group the various materials that are able to incorporate and incorporate reversible lithium-ion batteries into big families, the so-called electronegative materials and the electropositive materials. The combination of an electropositive and an electronegative materials leads to a electromotion force of the corresponding lithium-ion batteries, and this means that we can extract work from the cell. Obviously, the goal is to minimize the operating voltage of the electronegative material and maximize the operating voltage of the positive electromaterials, while in the meantime we need to improve as much as we can the theoretical capacity of the 2-1 in order to have the largest amount of charges exchanged in the cell. If we tackle and break the ice with the state-of-the-art negative electrode material that is graphite, we can see that graphite has an honeycomb layered structure formed by layers of graphene sheets stacked along the C direction. This material is able to intercalate and deintercalate lithium ions through the so-called intercalation chemistry reaction. An intercalation reaction is a reaction in which ions are inserted into 2D layers that are breathing and they are not destroyed due to the reaction. Graphite, even in its very highly crystalline form in micrometric particles, can reversibly incorporate and incorporate lithium ions as shown in the voltage curve plot reported in this slide. In this voltage curve, we show the evolution of the cell voltage versus the real specific capacity in a cell when current is flowing. As you can see, compared to the redox potential of the reaction lithium plus 6 carbon that gives lithium C6, we have a smaller operating voltage in discharge and a larger operating voltage in charge. These two differences are related to the occurrence of overvoltages related to the motion of ions in the cell. There's a second feature that is very important to consider, that is the occurrence of reversible capacity. Irreversible capacity is the difference between the charge in discharge and the charge in charge. And this is due to the occurrence of parasitic reaction. In fact, at such a low redox potential that is very close to the one of lithium, there is no aprotic solvent that is thermodynamically stable. All the solvents that constitute the electrolyte of the lithium-ion cell are reduced at this very low potential. This reduction is a parasitic reactivity and takes place unavoidably on the surface of graphite. The good news is that this degradation leads to the formation of the so-called solid electrolyte interface SEI layer. That is a passivation layer that prevents a further degradation in the second and in the following cycles. This means that graphite is able to operate as a reversible electrode when the SEI layer is stabilized. Obviously, the goal of a real good material is to minimize this reversible capacity and to maximize the stability of the SEI layer. The second material that we are tackling is silicon. Silicon is a totally different material and doesn't work in lithium-ion cell through an intercalation reaction. First of all, its main feature is the very good theoretical capacity that is 10 times the one of graphite. This means that for every silicon atom, we can incorporate into the material 4 lithium atoms. This occurs through a no-lowing reaction in which the diamond structure of silicon is completely destroyed at the end. Moreover, a very large volume expansion occurs during the alloying. In order to preserve the structure of the material, because obviously the lattice is completely destroyed during alloying, we need to play with morphology. In fact, it has been demonstrated in the literature that a 1D morphology can handle this big volume expansion, and the use of pillars or wires electrode lead to possible reversible capacity that exceed 2000 mAh per gram, like is shown in the bottom panel on the right side, with a Coulombic efficiency that approach 100%. The Coulombic efficiency is the ratio between the charge and discharge capacity, and so if we don't have any reversible capacity, Coulombic efficiency, it reaches 100%. In this way, silicon is a very promising material, although obviously the handling of this very big volume expansion and the maximization of the loading on the material, on the electrode, are the main challenging point of the real implementation of this material in cells. Another very good material for lithium-ion batteries is lithium. It's another negative electrode material. Obviously, the formation and the redox reaction of lithium is very different from the two that we have tackled before. First of all, the very good news of this material is the excellent theoretical capacity. The way in which this material operate in lithium cell is through the so-called plating stripping chemistry, meaning that we have the nucleation of new particles of metallic lithium during discharge and dissolution of these particles of lithium during charge. This formation and dissolution occurs through the formation of dendrites. These dendrites grow during plating and are stripped back during the stripping. Again, like in the case of graphite, the main problem is the fact that at such a very low potential, lithium, of the operation of lithium, the electrolyte is degrading on the surface of this dendrite, and so after stripping, there's an empty shell of SEI layer called dead lithium that is left beyond the old dendrites. This dead lithium is accumulating cycle by cycle and obviously leads to the deterioration of the performances. In order to prevent this formation, various strategies have been proposed in the literature. The first, the most successful one, is the formation of an artificial SEI layer on the surface of lithium. This means that before the assembling the material into the cell, it is possible to cast over the surface of the metal a blend of a polymer, lithium salts, and additives that forms an SEI layer that makes the penetration of solvent to the surface of the electrode less effective and thus prevents the degradation of the electrolytes over the surface of lithium. Let's tackle the positive electrode material. The state-of-the-art material is lithium cobalt oxide. That is the material that is in all the smartphone and portable electronics. This material is formed by as a layered structure formed by octaedra of transition metal 06 units that are stacked within layers of lithium ions. The intercalation reaction occurs through an intercalation chemistry reaction that removes reversible lithium without altering the structure. This reaction is very reversible and very good up to the intercalation of alpha equivalent of lithium for each formula unit. If you go beyond, there's the nucleation of another phase, like is shown on the right side of the slide. This second phase, that is cobalt oxide, COO2, has a totally different crystal structure, and obviously the incorporation of lithium during discharge from this lattice is less effective than in the previous O3 structure. This leads to the incorporation of irreversibility. That's why lithium cobalt oxide can operate reversibly only for the intercalation of alpha equivalent and not for the full equivalent removal. Obviously, the control of the amount of lithium that is removed is very difficult, and in fact, cycle by cycle, irreversibilities occurs, and part of the material converts to cobalt oxide, and at the end, the cell fails because the positive electrode is degraded. The current challenges in the research for the positive electromaterials are two. The first one is the foreseeing of high voltage cathode material. If we improve the voltage of the operating positive electrode, we increase the net energy of a full cell. One option is this lithium manganese nickel oxide that is a spinous structure and operate at around 4.8 volt versus lithium, that is more than 1 volt above the state-of-the-art lithium cobalt oxide. This material operates through an intercalation chemistry reaction and is able to exchange one full equivalent of lithium. However, this very high redox potential is drawback, because at such high redox potential, the electrolyte oxidizes in part cycle by cycle, and the surface layer, that is a passivation layer that is forming over the surface of the material, is not able to fully prevent the degradation cycle by cycle. That's why the research is looking for coatings that over the particles of this lithium nickel manganese oxide, in order to mitigate or limit the degradation of the electrolyte and the accumulation of cumulative irreversible capacity. The last material that we are reviewing is the lithium-rich layered oxide. This family of materials tackles the challenge of high-capacity cathodes. In fact, this material is able to exchange one full equivalent of lithium, and thus breaking the wall of the theoretical capacity above 300 mAh per gram for a positive electrode material. This kind of materials is formed starting from lithium cobalt oxide by removing cobalt ions and substituting it with a blend of transition metal and lithium. In this way, the same structure of lithium cobalt oxides becomes more flexible and able to fully intercalate one equivalent of lithium. However, there's always an however, when we fully deintercalate this material, if we have a look, for example, of the most common stoichiometry for this family of material, that is lithium 1.2, nickel 0.2, manganese 0.6 O2, the fully deintercalated material has a stoichiometry in which, after the dilithiation, the formal oxidation number of lithium is +1, of nickel is +4, manganese is +4, and oxygen is unavoidably -1.7. This means that this reactivity is not a full intercalation reaction, but has also some oxide-peroxide chemistry that is occurring. In the long term, this shift of the redox reaction of the oxygen from -2 to -1.7 and reverse during the discharge leads to the reversible release of oxygen atoms and the incorporation of vacancies, in order to prevent the formation of too many vacancies. In this way, the material is degrading cycle by cycle, and this is the frontier challenge for this material. Thanks a lot for your attention.
Okay, now we move to section 2, the electrolyte, issues and beyond state-of-art perspective, presented by Dr. Francesca Colò, Politecnico di Torino.
In a standard lithium-ion cell, the third key component is the electrolyte. In general, an electrolyte is a solution of lithium salt dissolved in a mixture of organic carbonate-based solvents. This solution is soaked in a membrane which physically separates the electrodes and prevents short circuit. The electrolytes allows the lithium-ion transport between the electrodes. It should be electron insulating and electrochemically inert in combination with both the electrodes. We can divide the electrolytes in 5 main classes. Liquid electrolytes, gel polymer electrolytes, in which the liquid electrolyte is immobilized in a polymeric backbone, solid polymer electrolytes, where mainly the lithium salt is directly dissolved in a polymer matrix, inorganic solid electrolytes, such as ceramics and glasses lithium-ion conductor, and finally, the composite polymer electrolytes, which are hybrid materials resulting from the combination between inorganic solid electrolytes and polymers. Currently, most of the commercial lithium-ion batteries use liquid electrolytes, which have high ionic conductivities, allowing for fast charging. However, the use of these electrolytes is the main cause of the safety issues, like fire hazards, see the problems with smartphones, notebooks, but also electric cars, and low sustainability. These issues come from the chemical nature of liquids electrolytes that are based on organic solvents, which are toxic and volatile and are also prone to leakage. In order to overcome these problems, the scientific community is trying to move towards the solid-state chemistry. Of course, the requirements should be very close to the liquid electrolytes. This graph resumes the state of the art in terms of materials for solid-state electrolytes. In the center are shown the most popular polymers, from polyvinyl fluoride to polyacrylonitrile to the one that is considered the father of polymer electrolytes, PO. It is possible to combine some of these polymer matrix with inert ceramic fillers or fast ion conductive ceramics. Or we can use these conductive ceramics alone, but we have to count that there is a limitation in the cell design. The possibility to construct a solid electrolyte are very wide, but we have to work hard for reach the same. It is not obvious. Among all the different solid-state electrolytes, polymer electrolytes are very appealing for their characteristics, such as the simple preparation procedure and the possibility to be designed in several shapes, flexibility, and so on. The most popular polymer matrix is polyethylene oxide, PO. During the 70s, Wright and co-workers demonstrated the capability of ether-based polymers to dissolve inorganic salts and exhibit ionic conductivity at room temperature. During the same years, Professor Arman poses PO at the center of his research on polymer electrolytes. The problem in using pristine PO is that it can work above its melting temperature, and the formation procedure of the membrane, such as solvent casting, is time and energy consuming, and makes use of organic solvents which render it non-eco-friendly and less efficient. As ion transport was considered to occur only in the amorphous region, the research community investigated only polymers having a low glass transition temperature, so that at the standard cell operating temperature the material is in the rubbery state, and the ion conductivity is similar to the liquid-like conductivity. In order to reduce the glass transition temperature, for example of PO, the really simple and fast preparation procedure is UV curing, which we use in our labs and is also possible to transfer to the industrial scale. Composite electrolytes are solid polymer electrolytes with submicron or nano-sized inorganic particles dispersed in the polymer matrix. Adding inorganic particles induces a favorable interaction between the ceramic surface states and the anions of both the lithium salt and, for example, PO segments, thereby promoting lithium-ion transport and inhibiting polymer crystal-like formation. This results in enhanced ionic conductivity, promoting interfacial stability at the lithium metallic electrolyte interface, suppressing the growth of dendrites, improving mechanical properties, and increasing lithium plus transference number. Another important class of solid electrolytes are the solid inorganic materials, including ceramics and glasses, which present high lithium ionic conductivity at ambient and subambient temperatures. Particularly, superionic conducting ceramic have impressive conductivity values and are single-ion conductors, allowing the lithium transference number to approach unity. These characteristics and the absence of leakage make the inorganic electrolyte a highly appealing electrolyte material for lithium-ion batteries. However, when used in the form of pellets, they are brittle, which makes incorporation into a battery difficult. Since polymer electrolytes have the softness and flexibility useful in a battery, but their transport properties tends to be inferior to inorganic superionic conductors, the scientific community thought moving towards the combination of polymer and inorganic materials. These resulting in hybrid electrolytes which are mechanically stable, with the softness of polymers at the surface of the electrode to enhance the active material utilization and the remarkable ion conduction properties of ceramic. Thus, there is a growing interest in composite electrolytes with inorganic and organic phases in intimate contact. Most of the systems studied recently involve inert ceramic particles and PO with the possible addition of lithium salt. For example, by incorporating LLMNO, we were able to fabricate mechanically robust composite electrolytes with ionic conductivity approaching 10-4 Siemens per centimeter at ambient temperature, which allowed stable cycling at ambient temperature, as well as by the use of LAGP, Nicicon type ceramic, we obtain a huge improvement in the cycling performances compared to bare PO-based electrolyte. Summarizing, the future development direction of polymer-based solid electrolytes is likely to be the homogeneous combination of fast ion conductors and polymers, which can combine the advantages of high ionic conductivity of fast ion conductors and solve the problem of poor interface contact. The difficulty in polymer inert ceramic solid electrolytes is how to construct a good dispersion and strengthen the interaction between the filler and the polymer, which restricts the improvement of ionic conductivity. If this will be solved, composite solid electrolytes will gain all the advantages and are, in our opinion, the direction of development of commercial solid electrolytes.
And finally, the last section of today's webinar, the industrial viewpoint and perspective by Dr. Matteo Destro of Lithops Batteries.
Lithops is the first lithium-ion research lab in Italy, established in 2010 in Turin. In 2016, we became part of Ser Industrial, an Italian group with more than 600 employees, with strong focus on circular economy. Lithops is responsible for lithium-ion cells development within the FAAM Research Center. Here in Turin, we are developing the technology for cells production in our pilot plant, where we can produce prototype cells starting from the active materials. Thanks to the flexibility of our pilot line, we are also involved in several European-funded projects, and this helps us to develop a strong collaboration network and to follow the state of the art in research. We are actually finalizing the installation of a plant for lithium-ion battery production in the south part of Italy. The production capacity should reach 300 megawatt-hour per year. The investment of 55 million was partially granted by the Italian government. We aim to a niche positioning in the market, and the applications are in stationary storage, industrial traction, and some specialties. We have recently been selected for the EPCA project to implement our plant, bringing the capacity to 2.5 gigawatt-hour per year, moving the technology to generation 3B and 4, and moving the application to the automotive market. But this is a long-term project that will start at the end of this year. If we have a look to the value chain of a lithium-ion battery production, we can summarize our perspective on where the research can have a strong impact. There are still a lot of points in the production that must be optimized by the manufacturers. But I also think that a deep collaboration between academia and production should be strongly encouraged, and that the manufacturers should try to develop this collaboration by stating clearly which kind of inputs we need from research and which are the most important points to focus on. Today, I would like to point your attention on three main topics. First of all, we must consider that the materials we select are going to have an impact in the whole production. We should not focus only on the performance, but also take care of the environmental impact of our choices. Secondly, as manufacturers, we are interested in developing new and smarter production processes. For example, favoring solvent-free process if possible. Last but not least, the recycle is a fundamental point to be developed in strong collaboration with lab-scale research. The first topic I would like to highlight is the material selection. As we can see from the graph on the left, reporting the production cost per cell from important manufacturers, the materials are impacting for around 60 to 70%. If we look at the detail on the right, we will notice that the cathode has a major impact, like 22% of the whole production cost. Cathodic material is definitely the key factor in terms of ratio between cost and performance. This is the topic where we believe that basic research can give a strong boost to the industry, together with the work on solid electrolytes. The roadmap from European Commission on the right regarding materials for future batteries comprehends high voltage cathodes, silicon-based anodes, and solid electrolytes. These are surely the frontiers topic where research will focus for next years, together with the use of lithium metal as anodic electrode. From a manufacturer point of view, I want to highlight that the performance is not enough to properly evaluate the materials. We must all start to consider other key parameters. For example, the cost, the safety, the temperature stability, the manufacturability. I also strongly believe that the final application must be taken into account because we now have a lot of different materials to play with. And the customer interest for tailor-made batteries is recently growing very fast, and we must understand that a big part of our added value could be the ability to find the proper materials mix for a specific batteries and their application. Another feature of material selection to point out is that we should seriously start to play on the selection of inactive materials, for example, by replacing the use of organic solvent with water, or by adopting eco-friendly materials for packaging, also taking into account the final recycling of the battery, with the aim of a circular economy. As a manufacturer, it is mandatory to start reducing the use of cobalt and other toxic materials, as well as to start to consider the source of the material we select and its impact on the ambient. The environmental footprint of lithium-ion batteries could be strongly reduced when acting on the production process. During last years, several studies reported that the battery production process is the major contributor to the energy used during a battery life cycle. LCA studies are becoming a fundamental support tool for the design of novel smart production processes that must take into account the environmental footprint, where the manufacturing is normally cost-driven. We have to start considering on which step of the process we can all have positive impact, starting from the point that any process needs input, like materials, energy, and resources, and gives products out. but also waste. We should consider the source of raw materials we use and its environmental impact. We should also work on new synthesis methods, favoring solvent-free choices and energy-saving synthesis that reduce the cost, for example, with low pressure and low temperature features. Regarding the electrodes production, we must reconsider the whole production process, taking into account not only the cost, but also the waste produced, the emissions, and the water consumption. If we exclude material preparation from the production process, we can see, as shown in the bottom right, that the main part of the energy consumed is used for drying and to run the dry rooms where the activities are carried out. We can reduce this energy demand by replacing organic solvent with the use of water, that would also reduce the environmental footprint of the whole process. The amount of energy spent for drying can also be reduced with novel coating technique, capable to reduce the solvent content, and consequently with easier and faster drying step. Another process that must be optimized is the formation and aging step, that is generally time and energy consuming because the cells are kept inactive at high temperature for several days. Manufacturers are looking for any way to reduce this time or to deal with the energy consumption. For example, in our pilot plant, we are going to exploit the heat emission coming from the other processes to reach the desired temperature in the aging room. The last point I want to talk about is the recycling. When we are talking about recycling, we are dealing with the end-of-life treatment. Before recycle, we should consider the possibility to exploit each battery for a second life. But even considering a good second life, we are expecting around 300 million cells at end of life in 2030. If we look at the expected consumption trend for metals and materials for lithium-ion batteries, in particular for lithium, it is quite evident that we must put a lot of research effort in develop reliable recycling processes. It's a matter of cost, obviously, but also of environmental footprint and global socio-economical balance that we should all start to take into account, starting from our work in lab research. If we consider that almost 85% of the materials in a cell are expected to be recoverable, it becomes clear that we must enhance recycling to become the most important source for materials for lithium-ion batteries. Recycling process consists of three major steps: pretreatment, normally a mechanical process, then mechanical extraction, and the production preparation. To reach reliable recycle, basic research and industry have to combine their expertise. There are still a lot of challenges to be faced. First of all, we need standardization that are nowadays still missing. Then we must organize the whole end-of-life process with an efficient collection, optimize the logistics with sorting protocol and an efficient second life reuse. We should also go back to battery design, even to material selection, looking for eco-design that should allow to facilitate dismantling and recycling of different battery formats. We must develop recycling process able to recover almost all the materials of lithium-ion batteries without high purity, because we all know that we need battery-grade materials to produce batteries.
And now I think that we all ran out of battery, so it's time to conclude by thanking you all for being here with us attending this webinar today. Special thanks go to Paul and Nicholas for their continued support in the last weeks and for optimal setup. I would like to thank again the speakers of today, Dr. Colò, Professor Brutti, and Dr. Destro for participating in this webinar. The speakers are at your disposal to answer any additional questions and curiosities. Kindly contact them at the email addresses you see here on the slide. Now, in the following two slides, you have a list of references retrieved from the international scientific literature. By definition, it is partial, of course. It does not have any ambition to be complete or exhaustive, but simply a reasonably limited list that offers a sufficiently comprehensive overview on lithium-based battery research. Now, thank you again, and be back soon after for question time live. And now, question time. In the following slides, you will have the answer to the question that have been raised by attendees of this webinar.